Hi, so very good morning to everyone. Welcome back to day 2 of the STEMS qualifier camp. We hope you had a great time yesterday and will continue to do so today as well. So to kickstart today's talks, we have Professor Sujay Ashok from the Institute of Mathematical Sciences, Chennai with us. Professor Ashok obtained his BTech from IIT Bombay and his PhD from the prestigious Rutgers University in 2005. So his research interests include string theory and integrable systems. Uh, Professor Ashok has given many talks at conferences all over the globe and has also been actively involved in organizing conferences. So just a quick instruction before Professor Ashok takes over. Please turn on your videos if possible so that we can come closer to having a physical session. Today, he'll take us through an exciting journey through the so-called principle of least action. So we hope all of you enjoy. Over to you, sir.
Okay, thank you very much. I want to thank Anirudh and Amik for all their organizational efforts and for not taking no for an answer many times. They're very persistent. So as he said, the title of the talk is Principle of Least Action. I hope to explain at least what this means by the end of the talk. So I just want to say that, please interrupt whenever you have any question, whether if something is not clear, because it'll really help. Otherwise, I don't know really how the talk is being received. So it'll be great to have some feedback either in the chat or, just by unmuting and asking questions that you have. Okay, so let me start by saying what this talk is not about. Okay, so I was told that earlier, yesterday you had a talk on percolation. So, I will not discuss any particular phenomenon like that, or I will not try to explain any particular thing. So these are examples of questions that I wish somebody had given a talk about so that I would understand it better. But, my idea of research is quite mathematical. So instead, I thought what I'll do is to explain one aspect of how theoretical physicists study theories. So this principle of least action is a very deep and fundamental idea, and it's sort of all pervasive. So I thought it'll be nice to share this principle of least action with you. Yeah. So good. So I want to first of all give credit where it's due. So these are not original thoughts, so to speak. What I will do is to summarize or paraphrase 2 lectures from Feynman's lectures on physics. So I will again flash this slide at the end of my talk. So if you so as a reference, there's one thing you can take away from the talk. It's to read these 2 lectures. In case I'm not clear enough, he is definitely very clear in his explanations. So these lectures are, this talk is going to be a summary of these 2 lectures: principle of least time and principle of least action. Okay, good. So here's a brief outline. The talk has sort of 3 parts. So in the first part, I'll start at a very basic level. I was told that there are students from high school and also some undergraduates. So I want a little bit for everybody. So the first sort of third of the talk will be just an overview of what physicists know about various laws of physics. At least I'll just outline now. I won't explain in too much detail, but just sort of summarize what kind of phenomena are described by these things. We'll see various laws of physics. So then I'll pick one particular law of physics, which is very elementary that you might have seen in school, which is from the ray optics, which is just laws of reflection, laws of refraction, all of those things. And I'll show how to reformulate or derive those laws using what is called the principle of least time. Okay. Now, this part, at least these 2 parts, first part and second part, I'm hoping that everybody can follow the details as well. Because once you get this first part, the basic idea is what generalizes to the principle of least action. That will come to the third part of the talk. So, if something isn't clear in the first 2 parts, please do stop me, because otherwise the third part will be completely unintelligible. So please feel free to stop anytime. So let me start with my overview of classical laws of physics. Are there any questions about what I'm going to do now? Otherwise, I'll get started. Professor Rao is there. Hello, Professor Rao. Okay, great. So let me begin with my brief survey of laws of physics. Sorry. Okay, so the first set of laws that I'll overview is Newton's laws of motion. As we know, there are 3 laws of motion. The first one is what is called what introduces the concept of inertia, which is to say that objects at rest remain at rest. And if the object is in uniform motion, it will continue to remain in uniform motion unless an external force acts on it. Okay? Then the second law says what happens when an external force acts on the object. It says that if an external force acts, then the object experiences an acceleration, which means that its velocity changes as a function of time. And the acceleration is directly proportional to the force that acts on it. Okay. So the second law is what I will eventually rederive, so to speak, or reformulate in terms of the principle of least action. So just keep in mind that this A equals F by M, I will not say F equals MA, I'll say A equals F by M, is what we will eventually rediscover using a fundamental principle. And the last law is that every action has an equal and opposite reaction. Okay, so there's Newton there holding up a prism, and his great insight was to realize that these laws not only apply to terrestrial objects, right, but that it also applies to planetary motion. You know, these laws of motion are what are called universal laws. So they don't depend on where you are in space or when you do the experiment. But these also describe the motion of planets around the sun, for instance. And using just these laws, you can show that the motion of planets around the sun is an ellipse. Okay, so it's a rather striking and insightful set of laws. And I'm sure you've done plenty of problems using Newton's laws. Okay, what else do we know? So these kind of phenomena will be studied under the title of classical mechanics. You know, so these are classical theory, and it's mechanics. So how objects move in space and time, how they react under the influence of an external force, and so on. Okay, so far so good. Okay. So we also understand how objects or particles with charge interact. Okay, and these go by the name of the phenomena. These phenomena go under the title of electricity and magnetism. Okay, so this is the source of thunder and lightning that scared us when we were cave people, and it also explains the motion of currents in wires. You know, all of these things of magnets, how objects behave, of charged objects behave under the presence of a magnetic field. So all of these phenomena collectively can be solved by a very simple set of equations, which are called Maxwell's equations. And these two, hopefully you've seen some of things. For instance, you must have seen Coulomb's law. So Coulomb's law is part of Maxwell's equations. Okay. Then, so these classical forces and these Maxwell's equations are things that you might have experienced yourself. You know, if you might have been hit by a bicycle at some point in your life, or cars moving on roads, bricks on pavements, etc. Then there are other forces that you might not have experienced in real life, I mean, in your personal life, but are definitely there, whose effects are visible. So for instance, radioactive decay is something that you might have heard of. So these is explained by something called the weak force. Okay, it doesn't matter what it is, that there is some particular, and so it's a weak force, and there's another force called the strong force that keeps nuclei stable. So these are forces that act at an atomic level, let's say. So you need more sophisticated experiments to understand these better. But if you open a high school textbook, you will see these kind of 4 forces listed. Okay, there is these Newton's laws, there's electromagnetic force, or maybe the gravitational force that I mentioned earlier. So the gravitational force, electromagnetic force, the weak force, the strong force, and all of these things. Right. So what we want is not to have all these rules and regulations. What we want is one sort of simple principle that can, using which we can formulate all of these laws in a unified way. Okay, so that's our goal for the talk. So we won't study each of these forces individually. What we will try to understand is how theorists try to formulate these in a sort of single and unified way. Okay, are there any questions at this point?
Sir, I have a question.
Yes.
Sir, in this picture, what is being depicted and written as a colorful connection?
Very good. So this is the poster that came out when three physicists, David Gross, Franz Wilczek, and David Politzer, got the Nobel Prize for explaining the strong force. So they formulated a theory just called quantum chromodynamics, or QCD, that exactly showed that they explained how the strong forces act. Okay, you can Google this picture if you want. I think it's Nobel Prize in 2003 or something. I'm not sure. Yeah. Okay. Other questions or comments? So these are the brief overview of the fundamental forces of nature. Okay.
I think we're good to go.
Yeah.
I think we're good to go. Like maybe towards the end we'll get good.
Great. Sorry. Okay. Then there are some other laws that are not so fundamental, but they're sort of approximate laws. Okay. That work under a certain approximation. So so for instance, in ray optics or geometric optics, there's a law of reflection that I'm sure you've seen in school sometime. The angle of incidence is equal to angle of reflection, or the law of refraction that says that there is a particular relation called Snell's law that I'll explain afterwards, that relate the angle of incidence with the angle of refraction. Okay, so this will be our main example in the first part. I'll try to reformulate this simple law in terms of principle of least time. Okay, but the interesting thing is that the same idea also can be used to reformulate these fundamental forces as well. Okay, so I am hoping that that's the message that you'll take away, that there is a very nice way to reformulate many diverse sets of laws. Okay, so let me tell you let me just tell you what I just repeat what I just said, that these are examples of how physicists attempt to make sense of the world around them. Newton's laws of motion, these geometric optics, Maxwell's equations, weak and strong force, this theory of QCD I mentioned. All of these are various examples. And I hope to convince you at the end that the principle of least action is a very, very neat reformulation of all of these classical laws of physics. Okay, and I should say that it's not clear why they should be so. I mean, we're perfectly fine with all these laws. There's no reason why there should be a reformulation, but the point is that there is a reformulation. Okay, so it's interesting to think about why this is so. Now, at this point, I'm reminded of a joke that my colleague Dilip Jatkar from Harish Sandhar Research Institute used to say, that the principle of least action is basically the statement that all physicists are lazy. So you do the least amount possible. And statistical physics is an exception, because stat physics is a science in which of large numbers of particles, and that's where mob psychology takes over somehow. So that's an exception to the fact that people are lazy. Never mind. So please ignore this comment and let's move on to more serious things. So I should also say that the principle of least action played a very important role in a reformulation of quantum mechanics that Richard Feynman did in the 1940s. And as I'll show at the end, most quantum theories also begin with an action. Okay, and that sort of encodes all the data about your physical theory. So I've gone on and on about this action thing, and I haven't defined it. So it's not a very easy concept to understand. So what I'll do is to, as I said, postpone the action discussion to the third part of the talk. Okay, I'll conclude my review now, and I'll try to go on to some physics, which is the principle of least time that explains the laws of geometric optics. Okay. So this concludes my review. Let's go to the first physics section, so to speak, the principle of least time. Okay. So let me start with a brief comment about what is light. Light is what physicists would call electromagnetic radiation, and if we know that light has wave properties. Okay. They exhibit what is called diffraction. They can bend around corners. All of these things happen. And what we call light is a small spectrum of wavelengths. Okay, so light comes in all sorts of wavelengths, from the very small to the very large here. So it's a whole spectrum is there. And visible light is a very small component of this electromagnetic radiation that is there for all wavelengths. And depending on the wavelength, we know these by various names, like either AM radio or microwaves, or ultraviolet radiation or gamma rays, and so all of these are all light. Okay, and they all obey, as I said, Maxwell's equations. They are solutions to Maxwell's equations, what is called light. But for our purposes and for the next few minutes, we will forget this fact that light is a wave. Okay? And we'll draw straight lines or rays to indicate how light moves. Okay. Now this is an approximation. And this is an approximation that has a name. It's called geometric optics or ray optics. And it's a good approximation whenever the wavelength of the light that we're considering, it's very, very small compared to the size of the object. Okay. So the dimensionless ratio between wavelength of light, this separation between successive crests or troughs, is much small compared to, say, the size of the table over which it is going to refract. As long as that approximation is valid, we can forget about the wave nature of light and just draw straight lines to indicate the direction of propagation of light. Okay, good. So then there are two well-known laws of geometric optics. The first one says that, as I said earlier, it is the law of reflection, which says that if light hits an object, a perfectly reflecting surface like a mirror, then the angle of incidence is equal to the angle of reflection. So these theta I and theta R are these two angles. I couldn't figure out how to make a nice curve here either. So all my angles have the thing that you find in your textbooks, the arc that connects the normal to this line. So this is theta I and this is theta R, and theta I equals theta R. This is the first law of reflection. And the law of reflection is what is called Snell's law, which says that if you have two media, so if you have light going from air to water or air to glass or something, then what you notice is that the angle of incidence is not equal to the angle of refraction. So the angle at which these two angles are not equal, but in fact they're related. And they're related by this trigonometric relation. That sine of this angle of incidence over sine of the angle of refraction is a constant. So it doesn't matter how big the thing is, it doesn't matter. As long as it is much bigger than the wavelength of light, this constant is a constant that only depends on what material it is. So you see, this angle will change depending on whether I have glass or water. Okay, but as long as the same material, it's constant. This angle is constant. So these are the two laws that I want to explain by a principle. So is this clear? I hope you're familiar with this. Otherwise, just take it for granted that these are these two laws. Hopefully you've seen this in school somewhere. Are there any comments?
Sir, the refractive index that for the refraction will also depend on the wavelength or the color of light?
Yes, it can. Good point. Yes, but I'm keeping that constant for now. Let's see.
Okay.
So there are materials for this is true, right? Yes. I mean, the classic example is the prism, right? That's the first picture I showed with Newton holding a prism, where the white light will, reflect in different ways through the prism to give you all the colors of light. Exactly. Thank you.
Sir, in refraction, the frequency of the light remains constant. Why? But the wavelength changes. Why not the frequency changes in refraction case?
That would be some other phenomenon. I'm saying that I'm defining refraction for which this is true. Yeah.
Sir, frequency depends upon the source of the medium, right?
Source of the medium meaning?
I mean, it depends on the source of the light frequency.
Sorry, can you repeat what depends on this?
In refraction,
Yeah.
the frequency of the light depends upon the source from where it is coming. So it is
Sure.
always constant.
Yeah, so I'm just fixing the source. I'm saying take a given frequency of light to be really simple, right? And for a given frequency of light, I'm saying that these two are observations. So for instance, so people have documented, I think in Feynman's lectures, he mentions that Ptolemy had a table. Ptolemy, who had these theories of elliptical, what are they called? I forget what they're called. Some alternative theories of how planets move and so on. Ptolemy had tables of angle of incidence and angle of refraction and so on. And finally, it was Snell who discovered that these two are related in this way. So just take it for granted that there was thought a lot of experiments done for light of a given frequency, let's say. And these two were observations, experimental observations. So that's why we call them laws, So we observe them for glass, let's say, and then we say, is it true for water? It's still true. Good. So then we take various materials and see if it is still true. And people found that this is experimentally true. That angle of incidence and angle of refraction are related in this particular manner. Yeah, so let's just take this for granted. There are more interesting things to come. Okay. Good. So then, these two, as I said, these formulae agree with lots of experiments done by many people. You can ask, why does it work? Why should it be so? I mean, it's good to know such a law exists. It's excellent. But as physicists, it's always important to find a simple principle from which lots of consequences follow. So is there a single principle from which both of these can be explained? Okay, and this principle was formulated by Pierre de Fermat in the 1800s. And he said that, he postulated that, or he proposed that this happens because light is following the path of shortest time or least time. So you fix your...
Won't it be the least or the maximum?
Let's say least for now. I'll try to explain this better.
Extremum one.
We'll get there. Yes, we will describe extremum. Good. That's indeed correct, and we'll see why it is extremum. I mean, we won't see why. We will see that the extremum is what gives rise to this particular result. So you see, you're fixing the starting point when the light starts, and you're fixing the end point where the light is recorded, right? That where you see the light, and then Pierre de Fermat says, draw all possible paths from starting point to end point. Okay? Then light takes the path that takes the shortest time. Okay, it's rather amazing when you think about it. So you can even think, how does light know? Does it sample all possible paths? How does it know which is the shortest time? But let's take this granted for now, and let's see how far we can go with it. Okay. Good. So let's see how this works. Okay. So A and B. So this is the phenomenon of reflection. I start at A and I want to end at B. Okay. I mean, I want to end at B. And so I draw all paths. So what Fermat says is to draw all possible paths. So here I've shown you 3 paths where it hits the reflecting surface and reaches B. Okay. So here I'm making the constraint that at least it has to hit the reflecting surface before getting to B. There's also a path that goes from A to B like that. Those are paths that we're not bothered about. We look for all paths that go to the reflecting surface and reach the point B. Okay. Now we assume that light travels at a constant velocity in a given medium. So here the medium is only air, let's say. We are in this medium, A, B are in the same medium. So light travels at constant velocity, and we just list all possible times. And we indeed find that the shortest time here, the path of shortest time is the same as the path of shortest distance. Right? Because the time is nothing but distance divided by velocity, right? So velocity is constant, is essentially the path of least distance. So all you have to do is to figure out what is the shortest distance between A and B, provided it has to hit the reflecting surface. And we indeed find this thing. Okay. So you can ask, okay, how do you know this is true, right? Well, there's a very simple way to see how this works, which is to just fold this diagram outward. As in, you reflect about the you sort of reflect B about the mirror, okay? And what we end up with is this figure. So you see, I've just reflected B to B prime. And then you see that now I want to reach from A to B prime. Okay, forget about M. Now I only have air here. Right? And the shortest distance between 2 points is a straight line. Right? All these paths clearly have larger distance, and so light will take larger time to get to B prime. Okay, so clearly, Fermat had a point, at least. It looks like it's correct. So I hope I've convinced you that the principle of least time, which in this case turns out to be the same as the principle of least distance, tells me that the angle of reflection being equal to the angle of reflection is identical to saying that the shortest path between A and B prime is a straight line. Okay, so is this point clear? I'm hoping that you've seen this before at some point, but it's a very simple illustration of the idea that the principle of least time gives you the fact that angle of incidence is the same as angle of reflection. Okay? Okay, great. Now let's go to the harder problem, which is the principle of refraction. Now I want to use the same principle. I want to now conclude this trigonometric relation. I want to derive the trigonometric relation between angle of incidence and angle of reflection. Okay, so here I have to make an assumption. I want to say that while the speed of light in air is constant, and while the speed of light in water is constant, or air is or glass is constant, they're different. Okay, I'm going to say that. I'm going to give you a new definition of the refractive index. Earlier saying there was some constant that depends on the material, right? And now I'm going to say that the refractive index is the ratio of velocities of light, which I call sea air and sea water, in the two media. Okay. There's no reason why this n should be the same as that n that we saw at the beginning, but it will turn out to be the same. Okay. This is my first assumption. I'm going to assume that light is constant. The speed of light is constant in both media, but they're different. And secondly, that the ratio depends only on the two materials involved. Okay. Now, this problem should remind you of a problem you might have done in your mathematics course, which is to say that I have somebody drowning at B, okay, in water, and I have a lifeguard at A, and the lifeguard wants to reach the drowning person in the shortest possible time. Okay, and I'm sure you've done this problem. What is the path? What is the optimal path that the lifeguard should take to go from A to B in the shortest time?
The
Okay,
path light would take.
Sorry?
The path light would take.
Exactly. So I'm saying that that is the same question. That it is the same question that we are answering here. Because you see the velocity of light is constant here, velocity of light is constant here, but they're different velocities. So you see, you want to maximize the distance that light travels in air because its speed is faster in air. Okay, speed is faster in air compared to water, but it shouldn't be so much. The sea shouldn't be pushed too wide that the total distance is too great. So you need to do a balancing act between the distance in water and the distance in air, so that the time is as least as possible. Okay. So now I'm going to tell you something that the technical term for this is something that one of the students already mentioned, is the fact that this point C should be such that the time is extremized. Okay. So let me explain to you what that means. And this is the key idea that will generalize to the more complicated action case as well. This idea of extremization. What does it mean? So you see, what it means is the following. So here I've plotted the time taken by light. And on the x-axis, I've plotted where the turning point is. I mean, where the point at which it enters water. So this point C, sorry. So this point C is here. So I'm trying to move C around, okay, to see how the times change. Okay. And I want to find the point C at which it is the shortest time. Okay. And I'm telling you that what it really means is that any small motion away from C will cause an increase in time. If you go far away from C, time is definitely increased. But the fact that C is an extremum means that if you go a little bit away from C, just a little bit, if X is really close to C, then the time does not change. Okay, to the first order in the variation, which means that if I say X minus C, some distance small x, right? This distance, then let's call it delta X. Okay, to say that it's a really small distance. Then we are saying that to first order in delta X, the time should not change. So you're not saying that the dependence of time with X is like a V, but it's like a smooth curve where you want to vary it a little bit and show the time variation is zero. Okay, this is an important point. And the technical way to say this, using calculus, is the fact that the first derivative, which is the slope of this curve at this point at C, vanishes. Okay, but Feynman has this amazing proof in his book to say that, to show, which I'll talk to you next, to say that you don't have to do calculus. You can just really vary the time, vary the path a little bit, calculate the new time, and show that and demand that variation in time is actually zero. Is this point clear? This is the most crucial point of the talk. So if this is not clear, we'll stay for half an hour and make sure this is clear and forget about the action guy. So is this point clear? What does it mean to find an extremum?
So there are a couple of requests to repeat the point.
Excellent. I was hoping so. So I want to find the path of least time, right? And I'm saying that the path of least time is when the time is not only minimum, but is an extremum. Okay, which means that the dependence of time versus this location X where it enters the water looks a bit like this, looks like this curve. So clearly C is the minimum, you can see that if I plot what is the time for each of these points, you'll see that all of these times are greater than the time taken when the point is that enters the medium, the other medium is C. Right? Clearly it's a minimum. But it's not just the minimum, it is an extremum. That's what we are demanding. Which is to say that if I make a small enough change, I want the time to remain the same. To first order. I mean, if you take higher order things into account, as we'll see, it might change. But to lowest order, the times don't change. It's a bit counterintuitive. It's a bit counterintuitive because you might think, oh, if there's a neighbor point which is also the same time, why isn't that the extreme? But the point is, if you take into account more corrections to the time because you're far a little bit away, you'll find the time to be different. But the first correction to the time will be 0. Okay, the effect of moving away is higher order. That's what an extremum means. Okay, so let me show you how this works in practice. Okay, this is very cool. I think this is the coolest slide, and it's copied from 5-minute lecture, so I can't take credit, unfortunately. Okay, so here I've shown you the actual path, which is ACB, and I made a small variation which I've blown up for artistic effect, and so that you can see, I've moved C to a point X. Okay? And now I want to see what is the time taken for the guy to go from A to B, and how is it different how is the path AXB different from ACB? Okay. So here I've drawn 2 normals from X to this AC, and here from C to this point XB, to this line XB. So these 2 are normals, NAC and NXB. So you see, X is so close to C that these 2 lengths, AX and AE, are the same. We can assume that because they're so close to each other, they're like the arc of a circle. So these 2 lengths are like the 2 radii of an arc, of an arc of a circle. And similarly from B, if you draw a small arc from C to F, you'll see that these 2 lengths are the same. So time taken by light for these parts of the path are identical. Okay, AE, AX are the same, CB, FB are the same, right? So these 2 parts and these 2 parts, same time. So what is the only difference in the 2 paths? The only difference is that from E to C, the actual path moves in air, right? And the neighboring path moves in water. Okay. And we are saying that the first order variation should be such that these 2 times should be the same. Right? So time to cover EC in air should be time to cover XF in water. So this is the extremum principle at work. That small variation, time should not change. Okay. But time is nothing but distance divided by velocity. Right? So I've written TAC, TXF is just EC, the distance divided by the speed in air. And this time is XF, this distance in water divided by speed in water. But speed in water and speed in air are related by the refractive index. So these 2 lengths, okay, only when it is an extremum, remember, are such that they're related by the refractive index. You can see that EC has to be bigger because speed of light in air is more. You can travel a larger distance in the same time. Okay, so now I just do some basic trigonometry. I divide both sides by this common length XC, and I see that what I have is nothing but sine of this angle EXC. And here I have sine of this angle. Okay, but using just some basic trigonometry, you can check that that is nothing but angle of incidence and angle of refraction. So you see, just by using principle of least time, and really, as one of the students said, the principle that it's really an extremum, the fact that small variation does not change the time to first order, tells us that the angle of incidence and angle of refraction are related by this simple relation. Okay, at this point, your mind should be blown if you haven't seen before. From here on, the talk will just decay, and this is the high point of the talk. So, are there any questions about this?
So a couple of requests to repeat from why XF and EC are same.
Good.
Like the core part of the proof.
The core part of the proof is to say that, let me go back to the previous slide to say what we said. The core part of the proof is the statement that C is an extremum. which is to say that if I make a small variation from C, if I slightly change the path at which the point at which light enters water, then to leading order, okay, we'll see what that means later on, there should be no change in the time, right? The curve is sort of flat at the bottom. So if you make a small variation, you are still, the time does not change. This time does not change. Is that clear? That's the core part. So if the time cannot change, these two parts must have the same time. So remember that X is very, very, very close to C. I've just drawn it totally blown up. So if these two parts should have the same time, then the time taken by light to cover both paths is the same. First point. Second point, the only difference in the path is really EC and XF, because all other parts of the two paths are identical. Because you see, X is so close to C that these two are like two radii that are making an arc, which is XC. So if these two parts are the same and these two parts are the same, the only difference in the two parts is these two segments of the two parts. Okay, and extremum means that these two times should be, to cover these two different lengths, should be the same. That's why I have this guy. First order variation is 0, then time to cover AC is time to cover XF. And everything else is just basic geometry. So the physics is here, the principle is here, and everything else is basic geometry. Is it clear now? Hopefully it is clear. So you see, we'll repeat this for more complicated things. We'll choose something and then make a small variation and demand that nothing changes. I think I should move on, because how long is my talk, Anirudhan?
Like an hour and 15 minutes, with like an additional maybe like 15 minutes for
that
you think?
That should be enough. So is this point clear?
Yeah, I think people are happy in the
Okay,
chat
good.
section.
Now, for those of you who know calculus, I want a slide for them as well. So if you don't know calculus, just go get a cup of tea or something. If you know calculus, you see what we're saying is the following. I want to find out what is the value of X, this distance, this horizontal distance, for which the time is minimum or extremum, right? So all I do is to write the time to go from A to B as a function of this variable X. And that is just distance in air divided by velocity in air, plus distance in water divided by velocity in water. That's what I've written here, the first line. And the distance is just given by Pythagoras theorem. X squared plus y squared is this length square. So you see, I have this second expression here that tells me this is a function of X. And now extremizing means taking a derivative with respect to this variable X, right? And setting it to 0. And if you do that, you will just find that exactly the same thing we found earlier. That's the sign of angular
sign proportional.
I am missing some factors of 2. That's all, some half or something. Sorry. I could have written equality with the 2, but I was the principle of least action and I did the least amount possible for the talk. So I forgot. I'm sorry about that. Okay. So if you know calculus, it's just a simple differentiation problem to find the optimal X that minimizes the time. I mean, this is the extremization. And to minimum, you have to take the second derivative and show on that it looks like a parabola that is like that. Okay, so I hope the more sophisticated people and the people who are just care about the ideas, they're both happy about the fact that the principle of least time gave us both the amazing laws of reflection and refraction. Okay, so now physicists are still not satisfied. And as Feynman says, we can do more, in fact. You see, Snell's law does not tell you what the refractive index is. Whereas the principle of least time gave us a physical insight as to what is meant by what is this constant that tells you this that is dependent, that describes the law of refraction. That constant is the ratio of velocity in the two media of light, right? So clearly, if I take 3 media, if I take media 1, 2, and 3, like glass, water, and air, I can do a simple ratio, right, to show that the 3 refractive indices should be related in this way, because it's just the ratio of velocity of light. So C2 by C3 is just, C1 by C3 and C2 by C1, clearly, right? And each of these is the respective refractive index between a pair of media. So we find this highly non-trivial relation between the refractive indices of 3 media that you could not have guessed at if you just knew Snell's law, because Snell's law just said there is some constant, right? So the principle of least time, it's the ideal physicist's principle. It not only gives us a warm fuzzy feeling that we seem to have understood something about nature, but it also helps us to make a prediction as to what is the meaning of these things. That it's just not some constant, but that you can make a prediction and check that if you do an experiment with 3 different media, you can check this. Okay, so that's great. It's ideal. So now I hope this external principle is in your mind. Now let me go on to the more. So this is the second part of the talk is over. So I think this is a good moment to pause and take any questions we have before we move on to the more complicated stuff.
So there's one question in the chat. Looks interesting. So why does light slow down in certain mediums, and how can the explanation to this be used to support the principle of least action?
No, again, it was just if you remember, I just said, let us assume that A, speed of light is constant in media, and B, that, so speed of light can be measured and shown that it is, so that's something you can check. Why it is slower? It is slower. Yeah, see, it has to do, I don't have a simple explanation for this.
Will the permeability of the medium change due to that light permeability, permittivity?
Yeah, so you can measure some constants, that some properties of the medium to show that to conclude that the speed of light is, but I don't have an explanation at the level of this principle of least time. I would say that mostly you can conclude this from an observation. Okay.
Thank you.
You can ask if there are media where speed of light is faster. And I think if I remember correctly, you can engineer such media. But since I'm a theorist, you should never trust anything I say about an experiment. So I would, you can use Google Ceph to check. I'm sure people can have engineered such things where, you can have media where speed of light is faster. That's a good point. Yeah. But as far as, our limited arena of air, light, water is, it's clear that speed of light is slower in this media. So it's an assumption. Constancy of light is an assumption, but and it's an assumption that you can check. You can do many experiments and check that this is true. So that gives us an assurance that it's until we hit an obstacle and find an experiment that makes us revise our proposals, we will trust this. Okay, good. So other questions before I go to action.
Just one small question. So why extremum instead of minimum?
Well, it is what works. Okay, what can I say? Yeah, so you see, somehow the T of X is a smooth function of X in some sense. It's not like a V, it's not like a V where there is a discontinuity in the slope and so on. Yeah, I mean, I could have rephrased the principle of least, this Fermat's principle by just saying, as the other student wisely said, extremum, but I would have had to introduce a word that you wouldn't have heard before, maybe. So, yeah, the correct thing is the correct thing is always extremum and not the minimum. It is a good one-liner, as I say, but if you dig deeper, you'll find that it is not the shortest time, but it is the path of it is the extremal path, so to speak. So
it can be maximum also.
Yeah, if you ask me for an example at the top of my head, I don't have one.
A hemispherical, we will take a hemisphere from one point to another diametrically opposite point. The light takes the extremum point on reflection from that hemispherical surface, not the minimum, the maximum.
Tweak your experiment to make it maximum. I suppose. Yes. Yes. Good. All right, excellent. So we are poised to go to the principle least action. I just want to say that if you are in the 8th to 10th grade band, you might see several formulae that you find deeply disturbing because you don't know what it means. I would say forget about it. And I would say that you ignore the technical details and try to focus on what I'm saying and try to focus on the ideas involved. And I can assure you that the idea involved is no more complicated than the principle of least time. Okay, so good. So I want to again briefly revise Newton's laws. The usual approach is the following. I have a particle moving somewhere in space and time. I have lots of forces acting on it. I could have a gravitational force. Maybe the particle is charged. I have a Coulomb force acting, magnetic force acting. Everything. And I want to know, how does this particle move? Okay. And Newton's law says, well, at any given point in time, look at the trajectory of the particle, find what is the force acting on the particle, right? And that gives you the acceleration of the particle. So at each point, right, depending on how the particle is there at that point, the force determines how the particle moves. Okay, so just roughly speaking, the initial conditions and the force at any particular point will completely tell you how the particle moves. You see, but I want to say that this is a sort of a local question, in the sense that Newton's laws are local. It tells you how the force is experienced by a particle at a given point in its trajectory. So a simple example is given here, where the force is linear. Okay, it is proportional to the location of the particle somewhere. And if you don't know this, it's fine. Most forces can be derived from a potential. And the relation between the force and the potential is just a differentiation. Again, if you're not familiar, it's fine. Just think of the force. It's fine. Okay, so understand that this is the usual approach. Slightly in a more sophisticated way, what I would say is that a particle trajectory is some function. Okay, its position as a function of time. Okay, I also need the velocity as a function of time, and that gives you the whole curve. Okay, if you give me the location and the slope of at a point, I know exactly how it goes. And the acceleration, which is determined by the force, tells you how the velocity changes at any given point in time. Okay, so technically you would say that I want to solve this equation, which is called a differential equation. But if you don't know this, it's fine. It just means mass times acceleration is external force. Okay, so as I say, it's a local thing that you have to solve to get the whole trajectory, the global trajectory of the particle. Global means I know from starting to end point. So is this clear? This is classical mechanics, Newton's laws, formulated here in a slightly sophisticated way, where essentially it's just force equals mass and acceleration. Clear? Good. So now what I want to do is to rephrase it as an extremization problem. Okay. Now this is the variational approach. What is variational approach? I want to say, I fix my starting point at some time t. I fix my end point at some time t2. They're both given to you. I'm not telling you anything about the velocity. I'm not giving you anything about anything. The force is given to me, okay, or the potential is given to me. Let's say I know the potential at every point in space. I want to ask the question, what is the trajectory of the particle? Okay, so you see already that I'm not saying anything about what happens in the middle. I'm giving you the endpoints. I'm giving you the potential everywhere. And the question is, what is the path? And the answer is the path of least action. Okay, I'll tell you what this means. I'm just saying that, see, the question and the answer are just at a different framework from Newton's laws. It's a global question. I'm not telling you what happens in between and so on. I'm just saying, what is the path? Give me the whole path at one go. Okay, I've gone on and on about the action. What the hell is the action? The action is the following. The action is a number that you associate to every path. You see here, I drew several paths. And for every path, I assign a number, which is called the action. And what I mean by extremizing the action means that I find I say go through the list of numbers and see which of these numbers is an extremum. See, this should remind you of the time problem. See, light goes from A to B. There are many paths, right? Each of these has different times. The right path is the one that has the shortest time or the extremal time. It's the same idea. So the action is the following, that at every given point in the path, you compute the kinetic energy of the particle, you compute the potential energy of the particle, you take its difference. Okay. And then you sum over the whole path. That's your number. Okay, so here I've written it in English, Ke minus Pe, kinetic energy minus potential energy. Here it is in terms of equations. So this dx by dt is just the velocity. You can write it as half mv square, the kinetic energy, minus the potential energy at that point. Okay, so if you don't know what an integral means, let me give you a one slide review of an integral.
Sir,
Sir, what if the potential energy doesn't exist for that vector field, like the magnetic vector field?
It will be there. So for magnetic field also, you can have a potential formulation. It is not the potential you might be familiar with. So let me track back and say for all forces that have a potential formulation, I can do this. Okay.
Okay, sir.
Okay, so let's say I'm not discussing friction, for instance.
have
I'm
you
not doing frictional forces.
dx dt whole square? This implies that the particle is moving in one dimension, so there is only one path the particle can take
No. Why?
in one dimension. If the particle moves in one dimension,
So by path, I don't mean just the position. You see, it's x as a function of time. So if I fix the two points, starting end points, and say at time 0, particle is here. At time 10, the particle is somewhere else, right? I can have a path where it just goes like this. I can have a path where the particle goes up, down, and then go to the endpoint in the same time.
That won't be two. That would be two dimensional, not one dimensional.
No, same one dimensional. I'm just go forward, backward, go forward, backward.
Okay, I got it.
Right?
Thank you, sir. Thank
So
you.
no, this is a good point. The path doesn't mean the x at just x. It's x at t. It's very important at what time, what x you are. Okay, so I can have a path that that can be like a helix. I can have a path that goes round and round and round and then hits x of t. All of those are different paths. Okay, excellent question. I hadn't thought of that. Yes, good. Okay, so if you're not familiar with integrals, that's fine. What I do is I break up the time interval into various chunks, which I call delta t. In each chunk, I take the average kinetic energy and average potential energy, take its difference, multiply it with this time interval, and sum over each time interval. That's essentially what integration is. Okay. In the limit where this path becomes a smooth curve, I'll get the integral expression that I have. Okay, it really doesn't matter. All I'm saying is, for every path, I give you an action. Is this point clear? So let me just again, I'm sorry to bore the people who know this already, but I'm saying it now in English. At each point along the path, we calculate the difference between the kinetic and potential energies, time the length of the interval. That is the contribution of to the action from that interval. I add up all the contributions. That's the action for that path. And exactly like we did for the for the principle of least time, the true path extremises S. What that means is, if I take a path and make a slightly different path, right? The variation in the action should be 0. Okay, remember that curve, the t versus x that I had. It's flat at the bottom. So which means that a small variation should not change the action. Okay. So now let me tell you what is the difference between the principle of least time and the principle of least action. And the difference is the fact that the action is not a function, unfortunately. See, earlier we had t of x, right? The location at which the light entered the medium. That was just a parameter. Well, the difference is that the action is actually a functional, not a function, which means that it is a function of a function. So x of t is a function which tells you where the particle is at a given time. That's an example of function. But the action actually depends on the whole path. You see, it depends on what the function is. Extremizing a function is what we saw. It's very easy. But extremizing a function is more subtle, and it goes by the name of calculus of variations. It doesn't matter the name and so on. You can Google it afterwards. So what I'll try to show in the next few slides, I'm going a bit slow. And again, it'll be a bit technical next, but just bear with me. And hopefully you'll, by the time the punchline comes, you would have joined me in the path. Okay. So I hope the idea is clear. If there are any questions about the idea, please ask me now. Otherwise we'll be drowned in some details next.
So there's one question in the chat. What is the basic intuition behind defining action in such a complex fashion?
That's a good question. I mean, I think, yeah, I think there is no good intuition for it, in my opinion. That's why to me, it's a bit of a mystery. I don't want to give any fake answers. I think the ends justify the means, okay? And we'll see why it's a useful reformulation. At the end, you'll see just the reform. We'll get back Newton's laws this way. So in that sense, it's that way we know it works. It's just that once we have this formulation, it just becomes so much easier to generalize. We can apply this idea to many more cases than just Newton's laws. That's the power of the principle. Okay, the principle was, I think, originally defined just as maybe a mathematical curiosity. Maybe I don't know how. I think it was. I forgot to give references. I think the first person was Lagrange and various other people like that who reformulated this in this action.
Since it uses kinetic energy and potential energy, so is it somehow related to Lagrangian mechanics?
Of course. Yes, it is. It is.
Sir, I have a question. Sir, this principle of least action and principle of least time, are they used only because they agree with the experimental values, or do they have a deeper proof?
There is no proof of the principle of least action. As in, of course, principle. I mean, about why it works. The principle of least action can be used to check.
Yes, sir. Why it works?
Yeah, no, I don't know why it works. It's just, as I said, it's a very useful formulation, as I hope to come to the third part of the talk. But nothing I've told you should help you understand why this works. Yeah. Okay, so now let me go to some technical details. This is for the undergraduates probably. Otherwise, the school people can also try to follow, but try to keep track of the idea. So what is extremum? Okay, let's take a path x of t, and let's suppose it is the extremal path. Now I change my path, which means I change my path at all moments in time. Right? So the delta x that I've done here is different for each time. So I take one path and I make it into a different path that is very close to the original path, such that the boundary points are fixed. Right? At time t1 and at time t2, they're the same x's. Okay, those are called boundary conditions of my problem. So for any extremal problem like this, the boundary conditions are the most important. If you change the boundary conditions, you'll get a different thing. You'll get a different equation of motion. And the extremum is such that the action evaluated for the slightly varied path minus the action evaluated at the original extremal path is 0. Are you with me? Hopefully you are. Let me go on. Okay, this is the most horrible slide I have. I'm really sorry. I don't know what else to do. Or maybe the next one is worse. I don't know. If you don't know the details, it's fine. I just wanted to show you that everything can be done explicitly. Okay. This is the original action I said, the kinetic energy minus potential energy. The second one is the kinetic energy minus potential energy for the new path. So I see everything, wherever x appears, I replace it by x plus delta x. And because the delta x depends on time, it will also change the potential energy. I mean, it will also change the kinetic energy and the potential energy. And for simplicity, I've chosen a very simple potential, which is quadratic in x. Okay. And what I want to do is to just use the formula that you're all familiar with. A plus b square is a squared plus b squared plus 2ab. You can see that each of these is just a quadratic expression in the variation. And what I'll do is to just keep the linear terms in delta x. I'll forget about the delta x squared terms. That's what I mean by saying extremum. I want to make a small variation and demand that as far as the terms in delta x are concerned, nothing changes. Okay. Okay, so this is x of delta x plus x of x plus delta x expanded in gory detail. And we notice something that should be obvious, that you see these two terms are exactly the action for the original path, for the extremal path. Right? So when I do s of x plus delta s minus s of x, right? Only this term from the kinetic part and this term from the second term from the potential energy will contribute. Is that clear? And I have neglected all terms that are delta x squared. Okay, this is a derivation that you'll hopefully find in when you reach a university level in more in more careful detail. But the basic idea is very simple, that if I look at the variation of the action, it's an integral of this term. I just have two terms, one term that comes from the kinetic energy, one term that comes from the potential energy. And I don't know what to do with this first term, you see, because first term looks weird. I have a derivative of the variation. What I want to see is that, I see what the goal is to put this delta x on the outside of this bracket, so that I want to say that if that thing in the bracket vanishes, then for any small delta x, delta s will be 0. Right? That is my goal. To do that, I have to make use of the boundary conditions. It's very, very important. That's why I said that the this whole extremal thing for a functional only works if I tell you the boundary condition. This was never a problem for the principle of least time, where I had to extremize a function. But now that I have to extremize the functional, the boundary condition of the function is very important. Okay. Again, this step in the second half of this slide, if you don't know it, that's fine. All it means, all it shows is that if I have a, it is to show how a derivative acts using calculus. So derivative of a product of two things is just a derivative acting on the first term plus a derivative acting on the second term. Okay, this is what I've used. And if you use that, you can show that the first term can be written as this term, right, minus this term, or this term minus this term. Okay, I can write this term as the difference of two terms, one of which only depends on the boundary conditions, and the other one is what it is. Okay, so by this time, I'm sure I've lost lots of people. I'm sorry about that. The next slide, hopefully we'll come back to everything together. So the term that depends on the boundary condition, let's look at that carefully. You see, this term only depends on the endpoints. This is what I've shown here. If I do this integral over this term, you'll see that the thing inside the brackets only depends on the endpoints of the integral. And I've chosen my boundary conditions so that the delta x vanishes at both endpoints. See, this term I've written without any integral because it's the result of this manipulation. And this total derivative only depends on the endpoints. So delta x at t2 and delta x at t1 are 0 by definition. It's part of my problem. Therefore, this term doesn't matter. And now I have what I want, which is to write this variation of the action as the integral of some quantity, some local expression times the variation itself. I know that I haven't said anything about the variation. I have a path. I made a delta x variation, which is arbitrary, but small. So I have a path that is arbitrarily close to the extremal path. And I want delta, that variation to be of the action to be 0. And the only way to satisfy that for arbitrary delta x is if this bracket vanishes. And that bracket vanishing is exactly Newton's laws.
Could you please go back to the previous slide once?
Please. Are you writing down notes? I mean, these slides are freely available for you. I mean, I've sent this to the organizers. You can ask it of them. I would say don't worry about the details right now. You can look at it afterwards, more carefully. Did you have a question or did you just want to look at the slide? Okay, never mind. So can I go ahead, guys?
Yes,
okay,
I think we're good. Yeah.
Okay, so I've reached the end of the derivation, which is to say that the extremum of the action is such that the path follows Newton's laws locally. See, this is at any given time in t. See, so we have derived a local law from a global requirement. So the extremum of S is the path along which Newton's laws are obeyed. That's the punchline. I hope, at least if the details are not clear, at least I hope the idea is clear, and I hope you are with me. Before I go on, so this is the last part of the talk as to why it is important. If you have any questions, this is a good moment to ask.
Sir, I didn't get how this integral reduces to md square x dt square equal minus kx.
Good. So you see, this term is the one that I wrote by integration by parts. So this term that happens on the left-hand side here, right? This term is exactly the first term here. You see that? So that term I wrote as a total derivative, which you can forget about, and this term, right? Because this term, this d by dt of this total, this term is just d by dt acting on the velocity times delta x plus velocity times d by dt acting on delta x. So that gave me the acceleration. Is that clear? So I wrote the velocity times the variational velocity as a total derivative minus the acceleration. See, and by itself, it's useless because you see, this term will still contribute. But because my variational problem, my extremal problem comes ready-made with a set of boundary conditions, okay?
Yes,
That
sir.
boundary condition ensures that delta x at the boundaries don't contribute.
Okay, sir.
Okay. So is this point clear? Can I go on to tell you why? So this, as some of you already said, what is the big deal? You know, I knew Newton's laws before this talk started. You've just gone and given me back Newton's laws and with the horrible functionals and extremization, all this nonsense. What does it buy us? You know, I want to convince you in the next few slides that it is extremely important because it gives us a new way to think about or new way to formulate theories. Almost every classical and quantum theory can be given an action formulation, and it helps us in the following way. The first thing it gives us, the first thing is important is because of this theorem that Emmy Noether proved in the 1920s, which is called Noether's theorem, which is to say that every symmetry of this thing that appears inside the action, right? So action I wrote as an integral over time of something, right? Earlier we had, you know, potential energy minus kinetic energy, right? So that thing is called what is called the Lagrangian of the system. Okay. So what Noether's theorem tells you is that the symmetries of the Lagrangian, which means if your Lagrangian doesn't depend on time, or if it doesn't depend on space explicitly, or if it doesn't depend on some angles, then every time that a Lagrangian has a symmetry, and I don't know if I will have time to explain what a symmetry really means, which means it's an invariance of the Lagrangian. I do a transformation on whatever appears here, and the action doesn't change. Okay, I should have really written symmetry with the action. I'm sorry about that, but it's okay. Every time you do that, you get a conservation law. Okay, so in your coursework, you must have seen, oh, energy is conserved in any process. In chemical reactions, you would have seen, you know, numbers are preserved, that is preserved, you know, these quantum numbers are preserved, whatever. Those are conservation laws, and they're very useful because they tell you what processes are not allowed. Okay, so every time you have a conservation law, it's a constraint, and that's great because it limits the possibilities of what we can explore, right? Or of, you know, it doesn't, you know, it helps us to not waste time, right? So this is, I can't overstress the importance. Is that the right way to say it? Yes, overstress. I cannot stress it more, so to speak. This is one of the most fundamental things that you have, Noether's theorem, that would have been only possible with the action formulation. See, if you just had Newton's laws, you couldn't have guessed at this. You would have stumbled upon the conservation law by accident. But using the action formulation, you can derive these conservation laws. You can see when energy is conserved, when it is not conserved. You can have an understanding of that. So it's a crucial component of all of modern physics. Secondly, you know, this gives us a way, and this is the sort of outer space kind of slide for you guys. This action gives us a way to incorporate all forces. This is what I said at the very beginning. You know, I have this force for gravity, I have this force for electromagnetism, I have this force for weak force, strong force. The action allows you to let go of these force formulation and just formulate everything in a single action. I can write down one action for gravity, electromagnetism, strong force, weak force, everything. So at a fundamental level, it's a nice, how would you say, it's a nice bookkeeping device, so to speak. Okay, everything you want to know or you don't know about your model or your theory that tries to explain your physical phenomena can be encoded in whatever you add terms with this action. So I don't expect you to understand this action doesn't matter, but I'm just saying that one can, in principle, write down a classical Lagrangian or an action for all forces. Okay, and that's a great unifying principle. You can just see everything at one go. I mean, of course, the laws you derive from this will be the laws of Maxwell, and will be the laws of Newton, will be the laws of whatever, of Einstein, and so on. Doesn't really matter. But I'm saying, this is why I said that this is how theorists think about their theories. The theorists, they think of an action formulation. Okay, so let me give you a one-slide summary of what someone do with the action principle. Okay, first you list what you want to describe. Okay, I want to describe gravitational force, I want to describe electromagnetic force, whatever. You make your list. Then, because I have Noether's theorem, I put into the action whatever symmetries I want to preserve. I will say that I'm not allowed to write terms that violate my symmetries, so and so. Right? I want whatever, some invariance under rotations, or I want invariance under translations, something. I just make up my own rules as to what I want my theory to be, to what my theory to respect. And then I just write down the most general Lagrangian or action that respects all of the symmetries. Okay, and this will automatically tell me which particles interact how. Okay, and all information about forces is now encoded in the parameters that appear in your action. Okay, so for instance, I had a potential kx squared in my earlier classical mechanics question. You can ask, what is k? Who gave you k? And the answer is nobody. K is what tells me how my particle interacts with the force. And I'll do an experiment to tell me what is k. And I'm telling you, this is exactly how people who work with particle physics experiments would do. They have their Lagrangian. They have all their terms that are appearing in the Lagrangian. And they have various parameters that they cannot fix because they haven't done an experiment. Okay. And the parameters are what appear as, for instance, in Coulomb's law, right? You have an epsilon naught that appears, or a k q by r squared, the k that appears there. Or in Newton's laws of gravity, you have this g mm by r squared, right? What is this g, right? Who gave you the g? No one does. The experiment will tell me what is the g, or what is that q, or what is that k. And all of those appear as parameters in such a Lagrangian. So I didn't write them here, but they are there. This v of h will have those parameters and so on. So at least as far as the classical theory is concerned, this is what you have to do. Okay, so I hope this helps you to understand why theorists work with action principles. So I have a few more slides for the quantum. Should I stop now? My time's up, but
I think we can go ahead.
Okay, so now I say, okay, all of this is classical mechanics. We know that nature is quantum mechanical. Is the action principle useful there? Okay, and the answer is yes. In the quantum theory, and if you haven't heard about this, it's fine. Just take a few messages away. At its heart, we know from experiment that nature is probabilistic. The quantum theory is probabilistic, which means that there is no sense in quantum theory to talk about the path followed by a particle from A to B. Okay, this question doesn't make sense in quantum mechanics. What you can ask is, what is the probability for a particle to go from one to the other? Okay, this is what you can measure in an experiment, for instance. But the probability for some initial and final state, the probability for some initial state of your system to go to a final state. That is what quantum theory tells you how to compute. Okay, and you can ask, okay, where is the action here? There's no action here. What is the point of this? And the old quantum theory indeed had some other rules to compute these probabilities that look nothing like what I just said. But indeed, it was Richard Feynman who realized that all of those rules of quantum mechanics can be obtained by a modified action principles. The modified action principle says that this amplitude that I said to go for the particle to go from A to B can be computed by summing not the action, but the exponential of the action over all paths. Okay, so you see now you should think back to what you must have had a thought. In the classical mechanics, you would have said, how does light know which path to take? How does it sample all paths? And in the quantum theory, is this Feynman formulation of quantum mechanics tells me that indeed, in the quantum theory, all paths are sampled, okay, and they are sampled with a weight exponential of the action. Okay, and this h that appears here, this h bar h, is Planck's constant. Okay, and this formulation allows you to recover all the old laws of quantum mechanics. And if you take the limit that the Planck's constant is 0, which is the limit when you should get classical mechanics, this definition tells me that indeed the action must be extremized. So you can recover the old action formulation from Feynman's quantum mechanical formulation for the amplitude. Okay, so the action is absolutely fundamental in all quantum mechanics, quantum field theories, in everything. And I think it's good to be exposed to this idea as early as possible. So I will stop soon. Let me just summarize and I'll stop. Okay, good. So as I said, all we did in the first 2 parts was to reformulate classical laws of physics in terms of an action principle. And my main motivation was to tell you that, talking about forces is fine. There's nothing wrong with that. But that there is an alternative formulation where we write down this action that incorporates all these forces automatically. And it's a very powerful reformulation because of the fact that we have Noether's theorem, that you can implement all the symmetries of your problem directly at the level of the action. And that not only is this true, this is useful at the classical level, it's also very useful at the quantum mechanical level. Okay. So before I end, I just want to say that I would like to acknowledge lots of people who gave very useful feedback. Eleonora de l'Aquila is my wife and collaborator, and she gave lots of important feedback. Dilip and Nikhil and Jan are my collaborators in my research work. And Ranjan, Madhusudan are my former students who are postdocs now. And Professor Sudhakaran is a historian. I just, for fun of it, sent him my slides, and he gave me several feedbacks, which were feedback that was very useful to reformulate my slides also. So I'll end there, and I'll stop with this reference. So please read the original. Don't be satisfied with reformulations. Yeah, thank you.
Oh, thank you very much, Professor Ashok. I must admit, you kept everyone going just by intuition. You kept everyone grasped with their attention. So hats off to you for that. It was an absolutely lovely talk.
Thank you.
So I'm sure there are quite a few people who have a lot of questions with the intuition you have given them. So I think I'll first post the ones who already have sent it in the chat, and the others you can unmute yourself and ask. So. So what's the intuition behind defining the Lagrangian as K minus PE?
Yeah, as I said, it's really the end that justifies the means. As in, if it did not give Newton's laws, I would have not taken it seriously. So I think originally Lagrange and others, I think it was Hamilton. I'm sorry, I should have missed Hamilton. It was Hamilton. It's also called Hamilton's principle, this extremization. So both of them, I think, only wrote potential energy minus kinetic energy because it exactly gives Newton's laws. We know the Newton's laws work, right? There's no doubt about that. So if it did not give Newton's laws, it wouldn't have, we wouldn't have been talking, we wouldn't have had this talk. So the correct Lagrangian is one that gives Newton's laws. So yeah, for more unfamiliar systems, indeed, the only guiding principle are these symmetries. What is it that gives us? It's indeed the symmetries that give us. So this is a good question. In fact, it can only be truly answered if you know relativistic mechanics, because all of these Newton's laws are non-relativistic mechanics, where we know the equations of motion. But really, in the relativistic formulation, what we impose is the fact that the theory should be invariant under Lorentz transformations. So there, indeed, we don't try to get anywhere. We impose this, and then we see that we get the equations of relativistic mechanics, which reduce to Newton's laws afterwards. But the original reformulation, indeed, it was a sort of answer analysis. The KE minus PE is answer analysis, in my opinion. But the reformulation in terms of relativistic mechanics is truly fundamental, in my opinion.
Okay.
There,
Excuse me, sir.
Yeah.
Sir, I'm Priyanshu Rai.
Yeah.
Sir, I wanted to ask, in the last slide, you showed us something called amplitude. What does that really means? Does it mean the total path covered, or?
No. So the amplitude is what? So you square the amplitude, right?
Yes.
Then what that gives you is, so the amplitude is a complex number. That's why I didn't give you anything for it. So in general, it's a complex number. Okay. But the absolute value square of that, which is the real number, gives you P, which is the probability amplitude for some process to happen.
Oh, okay.
Okay, so the amplitude by itself is not observable. What is observable is the probability.
Is the amplitude the wave function?
Sorry?
I mean, amplitude is that wave function that in the Schrodinger's equation appears as psi, like that.
No, this is more general. So here, my question is not regarding a wave function. Yeah, here it's just in this particular slide, what I've written is, I have a particle that goes from one point to another, right, at time t1 and t2 and x1 and x2. And this is the probability to go from this to that state. By state, I mean time t1 and x at t1.
Okay, sir.
Excuse me, sir.
Yeah. Yes.
Sir, can you provide a source for starting, means introduction to Lagrangian mechanics? Means it really seems difficult, but I want to start anyways.
What grade are you in? This is an important question.
Any source for learning about this?
What grade are you in? What is your...
completed my 12th.
Completed 12th. Okay, great. Then I would say that, I learned it from a book by Goldstein. I don't know if Kleppner and Kolenko has Lagrangian mechanics. They have it, right? The
maybe
is the one you should ask, because you see, I don't good classical mechanics. There are many books I can write. Off the top of my head, it's very hard to think. I would say that, yeah. So Goldstein's book is nice. I mean, it's standard.
Okay.
Kleppner, Kolenko is also nice, I think. But maybe I don't know. It depends on your taste. Landau Lifshitz is a nice book, but I don't want to give these sophisticated books to you guys. It's best to start at a base. I think Goldstein is a good book to read.
Okay, sir. Thanks.
Is the action integral same as work done?
I'm sorry. Can you tell me that again?
Yeah. B.V. Rao.
Hello, Professor Rao. Yes.
Yeah. Is the action integral same as work done in taking that path?
No. This is the one. No, I don't think so. No. It's just the potential energy minus the kinetic energy. That's the basic definition that you. I mean, for a non-relativistic mechanics, that's what I would say.
Okay, thank you.
Other questions or comments?
Okay, so if there are any other questions, I think you really can write to us and we'll get it answered by Professor Sujay. So, sure. Thank you very much. So please join me in thanking Professor Sujay for this wonderfully crafted lecture which he has delivered today. So thank you very much once again for that.
Most welcome. Thank you. Welcome.
Thank you, sir. So we meet once again today afternoon at 2:30 p.m. when we have Professor Xavier Vienna, The Art of Bijective Combinatorics. Hope to see you all there. Thank you.
All right.
Thank you, Professor Sujay, once again.